Good morning, sir. How are you today?
Very good, thank you. Very good.
It is such a pleasure to talk to you. I've been following your work for many years. I love your shows. And I love that you're revisiting some topics again. What brought you back to these particular stories?
Well, initially we'd thought that that there's so much. I can't remember how many series I've made now with the BBC, and there's probably 6 or 7 series, and it's been over it's almost 15 years actually. If you go back to the original Horizon programs that I did, and a lot has changed, particularly in the field that I'm interested in at the moment, which is black holes. We've had some absolutely tremendous advances. And so the idea came up that we would look back at those old shows, see what we'd said, particularly with reference to the cutting edge of our knowledge at that time, and see how it had changed. And also, I think, see how my opinion and understanding had changed over the years. Because, of course, in 15 years, I've learned a lot as well. And it's interesting looking back at old footage, actually, because sometimes I think, well, you know what, I'd have probably said that a bit differently, or I might even have changed my mind on a few things. So it felt like a nice idea. And then the idea came up that rather than try and cut it together and present, sort of stand out in front of camera and say things as I would in a big documentary, I had this idea that it might be more fun to do it almost like a conversation, like an interview. And so it's a very conversational link between those pieces.
It feels very seamless. Like the fact that you're jumping between some of your previous footage and new things, it does feel extremely relevant now as well, because so much has changed. Do you have one thing in particular you'd say right now that has changed the most, perhaps in terms of black holes, from when you first recorded?
Well, certainly in terms of black holes, if you go back even a few years, the great question was something called the information paradox, which is Stephen Hawking initially brought it up and believed that if you threw information into a black hole, so that, a hard disk or a book or whatever it is, then that information would be destroyed. So it would have disappeared from the universe. And you can see why, because black holes contain the end of time within them. There's this thing, the singularity, which is in a very real sense the end of time. So you throw a book, it goes to singularity, it's gone. But then, of course, Stephen also initiated the study of how black holes radiate. And they have a temperature and they radiate away. And so the question became, well, what happened to that information if the black hole isn't eternal? If it goes, admittedly on very long timescales, it just disappears into radiation and there's nothing left, then is it the case that the information that you've thrown in is imprinted somehow in that radiation? Or is it the case that it's been destroyed? And for many years, Stephen, actually, and others thought it was destroyed. That's problematic, profoundly problematic, because if you destroy information about the universe, then you can't predict its future. It's called determinism, right? So this idea is central to science, that information is conserved. It's not created or destroyed. And recently, in the last couple of years, we I think to most people's satisfaction, have solved that problem. At least in a sense that people now agree that information is not destroyed, that it comes out in the radiation. But the actual interpretation of what those mathematical results mean is certainly not agreed upon, because it's bizarre. And so people are talking about wormholes connecting the interior of the black hole to the far distant Hawking radiation that was emitted, billions and hundreds of billions of years ago. People talk about something called the holographic principle, which is the idea that that really it comes from the observation that the information seems to be in some sense stored on the black hole's surface, on the surface of the event horizon, and not in the interior. And in some sense, the interior doesn't seem to exist, certainly in some pictures. So all this tremendously advanced work on black holes and the information paradox has come about in the last few years. So I'm particularly interested in that at the moment. So that was a going right back to the first programs that I made 15 years ago, we touched upon black holes. But at the time, I think the richness of the description of them was just not apparent.
I love that you mentioned too that one of the most asked about things that you get is alien life, and that whole conversation, which is the first thing you cover in the new series.
Well, yeah, and that again, the search for exoplanets began really in the 1990s. Towards the time when I was beginning to make television programs, we started detecting exoplanets. So we hadn't detected any beyond the solar system when I was an undergraduate in physics. Now we have well in excess of 4,000. It's many thousands of planets we've discovered. And so the survey of planets beyond the solar system is now a real science. And that's changing dramatically. And now, actually, with the launch of the Webb Space Telescope in particular, we're going to be able to start analysing the atmospheres in detail of these things, and looking for signs of water vapour. And also then potentially, the golden scenario would be found oxygen in an atmosphere. When you find oxygen, the finger points to photosynthesis. So you can see biosignatures in the atmospheres of planets beyond the solar system potentially with the new, the new instruments that we've got. Back when I started making television programs, it was remarkable that we'd seen that the stars dim a little bit as the planets cross the face of the star. This is pre the Kepler Space Telescope. And so we really, that's been a transformation. And I find it very exciting. People talk even with it's kind of science fiction at the moment. But if you think about it, people have said, well, what would an industrial civilization look like? I mean, we know that changes the atmosphere of a planet. And the idea we're beginning to get to the point where we can analyze the atmospheres and therefore characterize the planets in such detail, even though they're, tens or hundreds of light years away, is to me quite astonishing.
It's amazing. It's wild to watch shows, because I've been watching science shows basically all my life. So it's wild to see where we're finally getting, and how much of shows used to be CGI because they had to be. And now more and more space shows have so much footage of planets and places we visited. Well, it's amazing.
Yeah, the solar system shows, when I made Wonders of the Solar System, which is the first big series that I made, we hadn't been to Pluto, for example. And now we've been to Pluto. So we see it. And, Pluto is a great example, actually, because every time we go to somewhere out on the edge of the solar system, or even moons around the gas giants in the outer solar system, I think before we get there, we just assume that they're barren lumps of rock. It's just our basic assumption. It's like our moon. Right, so nothing much happening there geologically. And you go to Pluto and you find out that it seems to have a heat source in its interior, probably radioactive. And we find a surface that looks new because it's not got very many craters on it. So people speculate about water, potentially liquid water below the surface of Pluto. So Pluto becomes a place where possibly you could imagine life, microbial life, for example, in the same way that we can imagine it now on moons of Jupiter and Saturn, that we had no idea that these would be potential habitats before we went there. And I think that's key, really. Our imagination tends to be less vivid than reality. It's certainly been the case with black holes. And as you say now, we have a photograph of a black hole now. I'm using photograph in a loose sense. It's a radio telescope image, but it's an image of a black hole at the center of a galaxy about 50 million light years away. You go back not quite 10, 15 years, but a couple of decades, and there was still a debate about whether black holes existed. I mean, they're predicted by Einstein's theory of general relativity, but certainly before the war, the Second World War, people really didn't think they existed because they're too absurd. It was actually Arthur Eddington's comments on it, the great physicist. He said that nature would not allow things so absurd to exist because the challenges they pose are so deep that you just think, well, it can't happen. And actually, it's people like Robert Oppenheimer very famous for the Manhattan Project, who first showed in the late 30s that probably a star with certain assumptions could collapse without end, right, to form what looked like a black hole. And then Roger Penrose got the Nobel Prize for that recently. So that was in the 1960s. He proved that with very general assumptions, you would expect sufficiently massive stars to collapse. So even that, it's in my lifetime that people managed to prove to most people's satisfaction that black holes might exist. But it's not really till the 80s or 90s, I think, that you really start getting this really firm evidence. And then only a few years ago that we get an actual photograph of one of the things. A big one, by the way, 6 billion times the mass of the sun. That one that we've got an image of.
For you, maybe you've answered this already, but for you, what is the biggest question that's been at least partially answered in your lifetime? What's the most satisfying, even, I'd say?
I mean, in my career, let's say my professional career, in particle physics, we hadn't discovered the top quark when I first started, which is one of the 6 fundamental building blocks of matter, one of the 6 quarks. And then the Higgs boson. The Higgs boson is a tremendous discovery, which my most cited academic paper is about physics in the absence of a Higgs particle. If nature didn't have a Higgs particle, what would it have? And that's my most highly read scientific paper. And of course, it turned out to be wrong in that sense, because there is a Higgs particle. So that's a huge step, because it's a fundamentally different sort of object in the, let's say, fundamental object. The Higgs boson is a fundamentally different sort of object in the universe. So that's interesting. Gravitational waves, the idea that there are ripples in the fabric of the universe that we detect from black hole collisions primarily, or neutron star black hole collisions. I mean, that I remember filming at LIGO, which was the gravitational wave detector, which subsequently again got the Nobel Prize for detecting them. And at the time when I was there, 15 years ago, I think, it was just a thing in a swamp in Louisiana. It wasn't particularly, it didn't look like the sort of thing that would turn into the high precision device that we've got now that's detecting, black hole collisions. It almost feels like every week. It's not quite, but the idea that black holes are colliding out there so regularly that every month or a couple of months we see the ripples in the fabric of the universe pass through the Earth and can detect them is astonishing. And as I mentioned before, black holes, one of the most interesting things about black hole research is that it's telling us about the structure of space and time. So the fact that what the black hole research is suggesting is that space and time are not fundamental, that they emerge from some deeper theory, some deeper structure in the universe. And it looks like that would be quantum entanglement or something like that. So it looks as if there are, you might call, atoms of space and time, or building blocks of space and time, which is really quite profound, because you need to know that. If you're going to really address questions about the origin of the universe, truly understand whether it had an origin in space and time, and if so, what was that like? Ultimately, you need a theory of space and time. And that's what Einstein's theory doesn't provide. So general relativity, for all its power, that takes as a prerequisite that there's this thing, this fabric of the universe. And I talked about gravitational waves being ripples in the fabric and all that. You really need to understand what that is. And I think we're beginning to knock on the door of that question.
In terms of your storytelling, I think it's one of the most fascinating things, because watching you on screen, you bring to life aspects of the story even before you've even gotten very far in. And I'm curious for you where that came from. In terms of science shows, your approach is kind of unique, I would say. At least it certainly has been over a number of years.
Yeah, I mean, I was heavily influenced by Carl Sagan. Cosmos was transformational for me because I was 11 or 12 when it was first broadcast here in the UK. And the thing that Sagan did, which some of the people I really strongly respect now in science and science communication, which actually people like Richard Feynman and Robert Oppenheimer, actually, I mentioned earlier, in 1950s, they were communicating in essentially the same way, because what they were doing was they were saying that it's not just the science, right? The science is, you can present what we've discovered. So we see a universe that's been expanding for 13.8 billion years, and there are 2 trillion galaxies in it, and these are wonderful things to talk about. But there's also, what does that mean? What does it mean for us? Could the way that nature forces us to think be applicable in areas such as politics, for example, or the way we can view ourselves in the universe, the way we treat our planet and ourselves, and so on? The question is, does science have an impact, or should it have an impact on those questions? The answer, of course, is yes. In my view, very strongly. But that's what Sagan did. Sagan's 13th episode of Cosmos is really a program about the threat of nuclear war, which was at the forefront of his mind back then when he made the program, the height of the Cold War, and the understanding our place in the universe, and understanding that it's very likely that intelligent civilizations are extremely rare, I think should have a bearing on the way that we behave and the way that we consider our, the way that we assess our value in a sense. So I think there's an element of polemic, rightly, in those kind of science programs, and that's what I try to bring. I try to, because I strongly believe that taking account and thinking about the things we've discovered about nature and the wider universe, and also going back to Oppenheimer and Feynman, deploying the thought processes that we develop as scientists in other areas is extremely important. I mean, Feynman said that science is a satisfactory philosophy of ignorance. That was his definition of science, by which he meant that when you investigate nature, even in experiments you do in high school, right? When you investigate nature, you tend to be wrong more often than you're right. And so you get a great experience with being wrong. And you learn to celebrate it, because you say, well, I've learned something, because I thought this thing worked like that, and it doesn't work like that. It works like some other way. And so that idea that being wrong is something that you can celebrate is profoundly important if we're going to make progress, not only in science, but in many other areas of society. Your storytelling also reminds me of something from the 80s. I don't know your thoughts on it, but there was a BBC series called The Day the Universe Changed. And I love just the way it presented. It went through a thought process of, we started here and here's where we are now. And the way it examined life, I think it reminds me a lot of what you're doing too, as well as Sagan's impact as well, obviously. Was that James Burke? I think it was James Burke, wasn't it? Yeah, he was brilliant. We had him as a guest on our radio program, The Infinite Monkey Cage. Oh, really? Honor, because you're right. He's still a brilliant broadcaster, actually. And actually, as you say that, the other another great example is Jacob Bronowski's The Ascent of Man, which is a superb. It's a science documentary, but it places the things we've discovered in a much wider context. And I think that's really important, actually. The science documentaries are not supposed to be a ghetto, right? They're not supposed to be somewhere that you just go if you want to find out what the mass of an electron is, right? It's a way of thinking about nature and our place within it. Do you think that popular culture has had an impact on the way we look at science now? Obviously, because of the Marvel Cinematic Universe and everything else, there seems to be a lot more science-y content, even if it's technically not science. Yeah. What do you think that's done? Yeah, I mean, I think it's a good thing, because when I was growing up, my time was Star Wars, right? 1977, those things, the first Star Trek movie. Not long after 2001, actually. Alien was another one. And they were tremendously influential, because I just knew I was interested in space. So I was interested in big questions. And if you're interested in big questions, then 2001 is a fairly good place to start, right? It's a tremendous exploration of what it means to be human in this vast universe. And I, so yeah, I think that science is too important not to be part of popular culture. And we can't be kind of sniffy about it. If I say that, and I believe it, which I do, then when it becomes part of popular culture, like you said in the Marvel Cinematic Universe, we can't say, oh, well, no, it's not like that. I don't want it to be in that way. I think it... The thing is, what's interesting to me is I get a lot of questions stimulated by those films. So, for example, the multiverse, right, is a question that emerges from Avengers Endgame and things, this idea of parallel universes. And there are a multitude of multiverses in modern science. So it's a way in to talk about them. And particularly amongst younger audiences, if I do live shows, then I get a lot of questions which are clearly stimulated by films like that. And that's a good thing because they make you ask questions, and you can ask things about which bit is real and which bit is not real, which bits are plausible and which bits aren't. So yeah, I think it's to be celebrated.
I love the fact that TikTok actually has a number of scientists on there, and some of the stuff that they talk about is so accessible and so it reaches a huge audience. And it is funny when you think of something like TikTok where the conversation is about music and dance moves, but you've got this huge contingent of scientists and experts talking about science on a major platform today.
Yeah. Yeah.
Have you thought about joining TikTok?
Yeah. I mean, I have, because we're going to... I'm doing some live show. I'm just writing them now, actually, some big live shows for next year. So I'll be in Canada and the United States, Australia, and so on. And so I've been looking at different ways to talk about that content and to promote those things. And you're absolutely right. TikTok is a good example. And there's something really wonderful about live interaction with an audience. I think that's really important because you get to find out what people want to know about. And also, if you explain something, which is often the case, in a way that doesn't really connect with someone, that two-way conversation often drags out a much deeper understanding, or sometimes will highlight a gap in my understanding. As I said, it's wonderful to be wrong, or wonderful not to know the answer. And it's really easy sometimes, I think, to dodge deep questions. And dodge things that you don't know. But you can't really do that in that format, right? You can't just wave your hands around and you have to say I don't know, and I'll go and find out. And the answer is yes. I think those formats are really interesting.
Well, and that's another question. I won't keep you too much longer, but in terms of this idea of presenting content when you're in a vacuum, where you're presenting to people you don't know who will be watching. How do you strategize the way that you're presenting that information? Like, do you have a method for testing that, okay, this people can understand this, or this is too obtuse, or how do you approach that?
No, I explain it in the way that I understand it. And actually, I'm quite slow quite often because I really do want to understand things at a deep level if I can. And so it takes me quite a long time. And I find that's a characteristic of many physicists and scientists that I respect, actually, that they seem to be a bit slow on the uptake, but it's actually because it's one of the crucial skills you learn. And I say this to undergraduates at the University of Manchester, where I teach first years. And I say, the key point is not to kid yourself that you understand something. It's really important that. Don't go, oh, yeah, just roughly. Yeah, okay, that's fine. I kind of get that. Don't do that. And what the way that you find out that you've done that in the past is by trying to teach it or explain it. So I explain it in the way that I have understood it, which tends to be quite pictorial, and I tend to be sort of less mathematical, actually, in the way with respect to some colleagues that. So I tend to really try to get pictures and verbalize to myself how something's working. And when you're talking about space-time around a black hole, it can be quite tricky, but that's why it takes me a while. But then I just say that. So then I just speak about things in the way that I understand them.
Well, the last thing I'm going to ask you, and you kind of approach a little bit of this in the first episode of the new show, but who are some of your heroes? Who are the people that helped shape you?
I mean, undoubtedly, I've mentioned Carl Sagan in terms of television and science. In terms of science itself, I mentioned Richard Feynman, who's always every physicist's hero in many ways, I think. But also, recently, I also mentioned Robert Oppenheimer. And Oppenheimer is an interesting character because I'd not really been aware of what he did, other than he's very famous for working on the Manhattan Project. But actually, in the 1950s, he gave a series of lectures called the Reith Lectures at the BBC. I think they're called Science and the Common Understanding. And they're a reflection on, as I said before, the way that nature forces you to think and the way that can be used in other fields. And they're brilliant. He's a tremendously deep thinker. And his science was, as I said, it was good. Certainly before the war, he was working on black holes and some of the fundamental physics around black holes. But after the war, he thought really deeply about the value of knowledge, the problems with the acquisition of knowledge and its distribution, obviously, because he worked on the Manhattan Project. So you think about those things. And he thought about them in a tremendously deep way. So Oppenheimer's become a real interest of mine, actually. And I've been sort of digging deeper into the way that he thinks.
And I know in the show you spoke to Frank Drake as well on the show. And
yeah, of course, yeah.
I didn't know much about him, so I ended up looking up a little, and he is a fascinating man. Yeah,
of the people I've met, I think, Frank Drake is. I mean, he's legendary. He, in terms of SETI, Search for Extraterrestrial Civilizations, he's, one of the names that just turned it into a science from idle speculation, and it's wonderful to meet people like that. The couple of Nobel Prize winners I've met are a bit like that. Kip Thorne, who I think is, he just written a textbook actually called Modern Classical Physics with Roger Blanford, which is an astonishing thing. If any PhD students are listening in physics, get that book, right? It's quite incredible that someone would have such a command and deep understanding of physics. So people like Kip Thorne. There's some, there's, I mean, another great, Jocelyn Bell Burnell that I met, that I got to know. She was extremely famous for detecting pulsars, right? So these sort of fast spinning neutron stars, which are one of the steps on the way to a black hole, actually. And it's interesting to talk to people like that, really great observational scientists who've made those big discoveries. So, yeah. Paul Nurse, he's a great Nobel Prize winning physicist, biologist. I elevated him to physicist. He'd be pleased to be. That's a joke. So, yeah, there's a lot of great people around.
Amazing. I'm going to ask you one last thing I forgot about. Because you incorporate adventure into your storytelling, I mean, what's the best adventure you've had? Because you've done some amazing things on camera.
Yeah, I mean, I sort of, reminisced about some of them. You're right, in this series. I think there's so many. One of the ones that really springs to mind, which is in the series, was the Soyuz landing that we filmed in Kazakhstan, which was quite tremendously difficult. Because the film crew got stuck in the snow, and myself and the cameraman ended up with the Russian army who helped us. So we had to leave all the crew behind. So we filmed that whole sequence with just a camera and me on sound. There's only two of us. And so it's a completely different way of making a documentary. But quite a lot of the film, which is one of my favorite films, actually, in a series called Human Universe. It's called 8-Man Spaceman, the film. And I just, that whole film actually was an adventure. We filmed in Ethiopia, which is one of my favorite places to film. You really get a sense. I suppose it's kind of one of those, it's a mythical thing in a way, but you because that's where we came from. That is the Rift Valley in Africa, where we came from. And you can, because of that, I think the place becomes very special. You can almost sense it there. And also, I filmed underwater in Star City, which is also, I think, in this clip series, which is one of the most difficult things I ever did. It's tremendously physically exhausting. So yeah, but the list is, I've been very lucky I think also in the series Alvin, where I go down into the really deep ocean.
I wondered if that was going to be one of your things, because it blows my mind to think of going down like that.
I think I said it's the closest I think I'll ever come to being in space, because it's the same, right? You're in a little ball with two other people, hours from the Earth, right? In a sense, it takes hours to come up from the deep ocean. In some ways, it's far more challenging in some ways. I mean, the pressure down 100 atmospheres or so, like that, a kilometer down. That's it's harder than space in some respects, and so I very much enjoyed that. Yeah, I mean, you don't get the chance to do those things. That's one of the great privileges, I think, of making television.
Well, thank you so much for the time. It really was a pleasure to talk to you. I'm a very big fan, so thank you very much. Have a great day. I can't wait to see the rest of the series.
Oh, thank you very much. Yeah, and how many have you seen? I've only seen one or two. Then there's there must be more to broadcast in Canada. And
well, the first episode I've seen, and it's fantastic revisiting some of this and new context. It's amazing.
Yeah. Oh well, thank you very much. Thanks. Nice to talk.
Have a great day. Thanks a lot.